morning. Today I am going to discuss the determination of Fourier series. Means Fourier series coefficients. So, determination of Fourier series means finding the Fourier coefficients, Fourier series coefficients of a given continuous time periodic signal. So this is my 14th lecture in this series on signals and systems. And yesterday in the previous lecture, I have discussed about the signal approximation and the introduction of the Fourier series. Okay, I have already given the introduction to Fourier series, and in this class, I am going to discuss about how to derive, how to find, how to compute the Fourier series coefficients for a given continuous time periodic signal. So here we have the Fourier series expression. So to recall, the given signal x of t, the given signal x of t is represented as a linear combination of a complete set of mutually orthogonal functions. What are those functions? e to the power of j k omega naught t. And these are harmonically related functions. That means you can say that these are also called as basis functions. So here, how many basis functions are there here? Infinite number of basis functions are there. Okay, k equal to minus infinite to plus infinite. It means we have taken the complete set of mutually orthogonal, harmonically related, complex, exponential or complex periodic signals. Okay, periodic functions. So I am trying to represent the given signal in terms of all these orthogonal functions. Okay, and in this one, I can rearrange the summation. Like this. What I am doing here, I am collecting all the positive terms one side and the negative terms on the other side. Okay, I am representing positive and negative as separate two terms, and the 0th term for k equal to 0 is nothing but a naught. Okay, so e to the power of j0 is again unity. So a0 e to the power of 0. So that is nothing but 1. So a naught plus positive terms one set and negative terms another set. So this is what I am doing. And we know that we have already shown in the previous class that the conjugate of ak, because ak is in general, in this representation, it is a complex number. Each coefficient is a complex number. So if you take the conjugate of this one, then it is nothing but f minus k. That means the a kth coefficient, a minus kth coefficients, both are conjugate to each other. So that is the significant part of this representation. And so what I am doing, I am substituting a to the power of minus k with a to the power of, ak star. A minus k, I am representing with, I am replacing with ak star. Okay. So by doing that, I have this. Now, if I add these two terms, I have to represent as real. It is a real part of this already in details I have given in the previous class. Now I am not going to discuss it again. So twice the real part of ak of this, and here you have to see that the summation has come out. Okay, the real part of each term I am taking. Now, so this is what, if I represent in polar form, this is what I will get. This is the compact representation of trigonometric Fourier series. So this also I have discussed previously. I am just recalling these things. And if I represent the ak coefficient in the rectangular form, I will get another equation. This is nothing but expanded I can say expanded Fourier, trigonometric Fourier series. Compact trigonometric Fourier series, previous one. Compact trigonometric Fourier series, expanded trigonometric Fourier series. Okay, I am giving different names for this, and these are all for real periodic signal. That means x of t is still real. I am not taking x of t as the complex. Now, so with this background, let us start our topic, that is determination of Fourier series of a periodic continuous time signal. So this is what the expression for the Fourier series expansion, and let us multiply this equation both sides by e to the power of minus j n omega naught t, both sides, left side and right side. So after multiplication, I have on right side this term, and on left side this I have this term, and this right side I have this term. Okay, so what I have to do, I have to combine this power and this power, raise it to e. So by doing that, this is what I have. Okay, so this I am calling this as equation 1. So here, what is this? E to the power of j in brackets k minus 1 and omega naught t. So k minus 1 is a difference between the k index and n index. That is what I am telling. And this bracketed term, I can expand like this. Okay, this is between 0 to t. One cycle period, first cycle period of the periodic signal I am considering. And if I consider this one, so from Euler's formula, I have cos plus j sine. So let us call this as a 2. So this is nothing but expansion of this term, that's all. Now, if you see the nature of this one, for k equal to n, what happens? For k is not equal to 1, what happens? If k is not equal to 1, this cos and sine terms are periodic signals, periodic sinusoids basically. What is their fundamental frequency? T divided by k minus n. Okay, k minus 1 absolute value you have to take, because it may be minus value or plus value, but the value is important for me. So 2 divided by the number difference between these two indices. Okay, so that is what we have to take. Now these are periodic functions. Okay, these are useful. If they are periodic functions, the area under the curve, periodic bipolar functions basically, I should say periodic bipolar functions. That is more important here. So positive areas you have, negative areas you have. If you over a period, one period, if you average, you will get 0. That is the significance of this periodicity. Now for k equal to n, if I take for k equal to 1, e to the power of 0. So integration 0 to t, unity here, dt. That is what on the left side I will get. And it is equal to unity. And if I integrate, I will get t basically. Okay, after substitution, after integration, I will get, this is 1. After integration, I will get t. So t minus 0, it is capital T. Okay, the integrand, this will become 1. But after integration, I will get a t. Okay, let us go to the next slide. So to summarize this, the left hand side of this, after substituting this 0 to t limits, I have, when k equal to 1, it is equal to capital T. That is nothing but period of the given continuous time periodic signal. And when k is not equal to n, it is 0. Okay, so this is what basically we have. And substitute this equation in 1. What is that 1? Go back and see. So this is 1, equation 1. So this is what your after multiplication by e to the power of j, e to the power of minus j, we got this one. Okay, so you can substitute in this and in this one. So what we will get after substitution? In equation 1. In equation 1, you are substituting this. So basically, when k equal to 1 only, it is t. Otherwise, it is 0. So see here, these are, so this is t. This part are shown as equation 3. Then, so this is a, ak is there here. And this ak equal to, and all other terms, see here, when k equal to n, so one term is there, all other terms are becoming zeros. So ak equal to this term. So that is what I have shown here. So ak equal to, because t is there here, so this t will come this side. So an equal to 1 by t integration of between 0 to t of x of t multiplied with the base, all basis functions, nth basis function here. Because, so what is the meaning of this one here? What I am doing here is to find nth coefficient, I am finding the inner product. I am finding the inner product of given function or given signal with nth basis function, nth harmonic exponential. That is what. Okay, I am multiplying these two, area under the curve. Okay, and area is t, so divided by t I am taking. So if I assume this as the energy, then the energy divided by time is power. So basically, this is the quantity which represents the power. Okay, so this much power is there. So what I am doing here is basically, I am finding inner product means what? Similarity. I am, every time I am multiplying with one basis function. For example, let us say a1. What I am doing with a1? So here also j to the power of e to the power of minus j1 minus j omega naught t. So what I am doing here? So I am taking the first harmonic, multiply with the given function, and find the inner product. That means area under the curve, and divide by t. So I am comparing this basis function, given basis function means first basis function for a1, comparing with the similarity between this and the given function. So if it is more similar, naturally I have this area more. If they are not similar, the area is less. So if the area is less means a1 coefficient is less. So if a1 is high, I can say that the given signal x of t contains first harmonic in a more proportion. Okay. Similarly, a4, let us say I will convert into 4. Then I have fourth harmonic here. So if a4 equal to 0, for example, let us say a4 equal to 0. Then what it means? a4, the fourth harmonic is not at all contained in this signal. There is no similarity at all. Similarity is 0. Totally dissimilar. That means this fourth harmonic is not contained in the given signal. So basically what I am doing, I am trying to analyze the given signal. Given signal is analyzed in terms of harmonics. Whether take each harmonic, whether the given taken harmonic is present or not. If present, how much quantity, how much proportion is present. It may be 1% or it may be 99%. We don't know. Okay, or 100%. So whenever the coefficient is high, corresponding harmonic is present in a big way, in a present large quantity in the given signal, basically. Okay, so I am decomposing the signal into different harmonic frequencies. So that is the crux. And here you have to see that Fourier series is the summation. Here, see here it is summation. Fourier series means summation. But still, when you want to find an, you are not using any summation. You are integrating this. So it is a continuous, because x of t is a continuous type. So the integration is over a continuous type. It is not at certain types. Okay. So don't say that here, because some people express some doubt on this. So this is summation, and when you want to find each term in the summation, you are using the integration, not the summation. Okay, because it is the continuous time signal. Okay. So now, since t is the integral multiple of periods of this, we obtain the same result if we integrate over the any other interval. That means, for example, let us say there are 3 harmonics contained in this signal. 3 harmonics are contained. So this is the t naught. 3 harmonics are there, and I have taken t naught, that is the overall result period of the result interval. And whatever analysis I am doing here, because it is again periodic. So this some combined signal is also periodic. So I can use some other period. Need not be always first cycle. Need not be between 0 to t. I can take t plus, let us say, some quantity, t plus t naught to t 2t plus t naught. Okay, that means between t and 2t, between 3t and randomly you can tell. See, what you want is you require one period of signal, that's all, because it's periodic anywhere you go. Sine wave, if we take one cycle, it need not be peak to peak, 0 to 0, or 45 degrees point, 45 degrees like that. So any point you take, you stop after one period. So automatically, so whether you do first cycle or randomly located one cycle period, it should not matter. So that is what is done here. So if it is possible, not only with one cycle, aligned cycle, you can take arbitrarily any duration, but the duration t should be equal to cycle period. You can randomly take in between the waveforms also you can take. Okay, so that's why that is notation is given as, if I put t here at the corner of this integral symbol, what it means is the duration considered here for this integration is somewhere. Okay, it is not a particular from between 0 to t. It is anywhere, but duration is t. So that is the difference between this and what about the other one? 0 to t. When I say 0 to t, you are taking first cycle only. But here, it is not first cycle, any cycle. In fact, it is not aligned with the cycle also. You are taking maybe half cycle somewhere in between the waveform, somewhere, and it is not the cycle period also. Whatever you have considered 0 to t, it is not aligned with that. Any period, from anywhere to anywhere, but starting to ending, it should be equal to one cycle period. Okay, so that is what is the meaning of this one. Difference between this and difference between this. So, in summary, this is AK and this is the given signal representation where each coefficient is given by this. So, this is nothing but your Fourier series. If I know coefficients, I have determined the Fourier series. So, let us take one example. X of t equals sin omega t, and is a simple expression, and sin can be represented with e to the power of j theta minus e to the power of minus j theta divided by 2j. So that is what is given here. Now in this, what is this? Here it is k equal to 1. So this is k equal to minus 1. So k equal to 1, only two terms are there here. A1, k equal to 1. A1 is there, A minus 1 is there. Okay. And for greater than 1, I have 0 coefficient. That means in this signal, only the first harmonic is present, nothing else. And what about the DC value A0? A0 is also equal to 0. That means there is no DC term in this. Okay. Now, take another example, a bit bigger example. First term, constant, sin omega naught t, 2 cos omega naught t, here cos. Okay, here if you see, this is fundamental frequency. Here 2 is there, amplitude is 2, but frequency is again fundamental frequency. Fundamental frequency sin, fundamental frequency cos. So both have the fundamental frequency only. And here 2 omega naught is there. So this is the second harmonic. Okay, so this waveform contains two harmonics. One is first harmonic, other one is second harmonic. And 0th harmonic, if I want to call, I have to call this as the DC term, is nothing but your 0th harmonic. Okay, so this is nothing but sin, and this is cos. This is divided by 2j. Here divided by 2 is there, but here divided by 2, and you had 2 here in this case. 2 will get cancelled. So I have this, and then here also divide by 2. It is there already because there is no 2 here to cancel. So half will remain as it is. Now you collect the terms, similar terms. What are similar terms? This is first harmonic. This is first harmonic. So what is this one? The scaling factor for this, the coefficient for, amplitude of this is 1, unity. 1 plus 1 by 2j. 1 plus 1 by 2j. Okay, this DC term is there anyway. So 1 plus 1, this is 1, plus 2j put together, first multiplied by first harmonic. Then 1, here it is 1, correct? So 1 minus 1 by 2j. Okay, so this is again first harmonic but negative frequency. Okay, then what about the other one? The third term, it is the second harmonic term. We have second harmonic, only 2 terms are there. Here half for the positive frequency and half for the negative frequency. Okay, both are these frequencies. Okay, now what is this? This is A naught. What about this? This is A1. This is nothing but A1. This is nothing but A minus 1. This is nothing but A2. This is nothing but A minus 2. Okay, so this is what you have. This is A minus 2. So this I have repeated here. And A not equal to 1. A1 equal to 1 plus 1 by 2j. And I want to bring this j, multiply numerator and denominator by j here. So I have j divided by 2j square. So minus 2 minus I will get here. So by simplifying I will get this. In the same way, a minus 1 is 1 plus half j. Then a2 equal to, by simplifying you will get this. This is nothing but this. So expand this. This is e to the power of j pi by 4. Okay. So this is pi by 4. So pi by 4 means it is nothing but 45 degrees. So you have cos 45 degrees plus j sin 45 degrees. So you have 1 here and j term is there, and after simplification you will get this. In the same way you will get this. And for k greater than 2, that means third harmonic onwards the coefficient is 0. That means this signal contains DC term, first harmonic and second harmonic only. Okay, which can be easily verified from this, because this is first harmonic and this second harmonic. This is DC term. Okay, now same coefficients, I take the magnitude of this one because coefficients are complex. So these coefficients are complex. If I take magnitude, what is the magnitude of this? 1, a naught equal to 1. See here, this is 1. This value equal to 1. Then what is A1? Magnitude of A1. A1 magnitude is this. What is this? 1 square plus 1 by 2 square. That is 1 by 4. So what is this? 1.25. Okay, 1.25. Yeah, 1 square plus, and of course you have to take square root here. So 1.25 square root, that is nothing but 1 square plus by 2 square root. Okay. So 1.25 square root of this is something you will get. So I think you have to verify whether actually this is correctly represented or not, because this is more, this appears more than 1 here. Okay. Square root of 1 is 1. Yeah, it is slightly more than 1. It is slightly more than 1. 1.44 means 1.21. 121 means 1.1. Okay. So it is approximately 1.12 something like that. Okay. So this must be 1.12 something like that. And this side also same thing, a magnitude of a minus 1. This side also I have 1.12 something like that. 1.11 or 1. Now if I take A2, what is the magnitude of this? A2 magnitude if I take. So this is what is A2. keep this as it is. What about this? Complex number only you have to find. So 1 square plus 1 square, square root of 2, square root of 2 and square root of 2. Multiplication gives 2, 2 by 4, 1 by 2. You will get 1 by 2. So this is nothing but 0.5 actually. This is 0.5 both sides. So this is what I can say. That means each line here in Fourier series, if you graphically represent, each line means each delta function, you can say. Okay. What is this? This is the index I am showing. What is the index? It is the number of the harmonic. It is the harmonic number. What is this harmonic? If I consider in terms of frequency, if I show here it is F0, 2F0, 3F0. So I am saying and this is amplitude of that frequency. Amplitude of that. So I can call this also as a Fourier spectrum. Fourier series spectrum actually. Okay. It is the frequency spectrum. So frequency spectrum means at each frequency how much it is present. So in this 0 to F0, between 0 to F0, no power is there. That means only F0 is. Below F0, no frequency. 0 is there. Between 0 and F1, no other frequency is present. So such spectrum, you can call it as line spectrum. Line spectrum. So line spectrum means it is different from, you don't say that, of course, line spectrum can also be called as a discrete spectrum, but a slight difference is there. So I reserve this only line spectrum for this kind of thing. So whenever you have a Fourier series expansion of a periodic signal always has a line spectrum. That means the frequencies at regular frequency intervals, that is harmonics are present. In between harmonics, no other frequencies are present. So this is can be called any periodic signal as only line spectrum. It cannot have all frequencies continuously. It can have only the harmonics of the fundamental frequency. Okay, so that is the important conclusion here. Now, so these coefficients are complex. So naturally, once you have the complex, you have the magnitude, which I have shown in the previous slide. You have an angle also. So what is this angle? A0 is a real quantity. How you find this angle? Angle of AK equal to tan inverse BK divided by AK. What is BK? First term is BK real part and AK is imaginary part. Okay, so tan inverse imaginary part divided by real part. Yeah, here of course I have reversed, I think. So let me correct this. So this is real part is AK, imaginary part is BK. That is how it is. Okay. So this is AK tan inverse. Now if I find like this, for A0, it is only real part is there. So the tan 0. Okay, imaginary part 0. So tan inverse 0 is 0. So I have see here. So this is nothing but angle. If I say that is what is shown here, angle of this one. So angle of this. This is angle or phase. Angle or phase. Phase angle. Basically angle means phase angle. And this side frequencies. Basically frequency. K it is shown here in terms of frequency. F equal to K F0. Okay. F equal to K F0. Kf0, multiple harmonics. So here, what it is showing here, this is the angle. If you see here, tan inverse half by 1, tan inverse half. So you have A plus 1 here, minus it is there. So minus angle, minus 30 degrees. My plus 60 degrees for A2. Here, for this. Okay. So minus 30 degrees. plus 60 degrees. Like that, you are showing the phase angle. General in terms of radians we will show. We don't show in terms of degrees. So this is in terms of radians. If I represent, I call this as phase spectrum. Phase spectrum of the given signal x of t. Okay, phase spectrum. If I take x of angle. What is capital X? So capital X, small x of t, and capital X of f both form Fourier series. Because I have not introduced a Fourier transform so far, so I call this as Fourier series. X of f is the Fourier series of x of t. X of t is the inverse Fourier series of the other. Okay, like that. So this is nothing but your phase spectrum. So phase spectrum exists at a discrete frequency. So phase spectrum and magnitude spectrum or amplitude spectrum. Sorry, this I should not use. So here this is nothing but x of f magnitude. So magnitude spectrum and phase spectrum both are line spectrum. If you can represent a periodic signal in terms of Fourier series. Okay, all periodic signals can be represented as Fourier series. So Fourier series means line spectrum, discrete frequencies which are harmonics are present, other frequencies are not present. Okay. So this is what you have. I will close this here because I have some more things to discuss. So along with that I will be discussing this. So thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.